The solar cycle or solar magnetic activity cycle is the nearly periodic 11-year change in the Sun's activity and appearance. They have been observed for centuries. The changes on the Sun cause effects in space, in the atmosphere, and on Earth's surface. While it is the dominant variable in solar activity, aperiodic fluctuations also occur. Definition: solar cycles have an average duration of about 11 years. Solar maximum and solar minimum refer respectively to periods of maximum and minimum sunspot counts. Cycles span from one minimum to the next. Observational history: the solar cycle was discovered in 1843 by Samuel Heinrich Schwabe, who after 17 years of observations noticed a periodic variation in the average number of sunspots. Rudolf Wolff compiled and studied these and other observations, reconstructing the cycle back to 1745, eventually pushing these reconstructions to the earliest observations of sunspots by Galileo and contemporaries in the early 17th century. Following Wolff's numbering scheme, the 1755 to 1766 cycle is traditionally numbered 1. Wolff created a standard sunspot number index, the Wolff index, which continues to be used today. The period between 1645 and 1715, a time of few sunspots, is known as the Maunder Minimum, after Edward Walter Maunder, who extensively researched this peculiar event, first noted by Gustav Sporer. In the second half of the 19th century, Richard Carrington and by Sporer independently noted the phenomena of sunspots appearing at different latitudes at different parts of the cycle. The cycle's physical basis was elucidated by Hale and collaborators, who in 1908 showed that sunspots were strongly magnetized. In 1919 they showed that the magnetic polarity of sunspot pairs is constant throughout a cycle, is opposite across the equator throughout a cycle, reverses itself from one cycle to the next. Hale's observations revealed that the complete magnetic cycle spans 2 solar cycles, or 22 years, before returning to its original state. However, because nearly all manifestations are insensitive to polarity, the 11-year solar cycle remains the focus of research. In 1961, the father and son team of Harold and Horace Babcock established that the solar cycle is a spatio-temporal magnetic process unfolding over the Sun as a whole. They observed that the solar surface is magnetized outside of sunspots, that this magnetic field is to first order a dipole, and that this dipole undergoes polarity reversals with the same period as the sunspot cycle. Horace's Babcock model described the Sun's oscillatory magnetic field, with a quasi-steady periodicity of 22 years. 2-3. It covered the oscillatory exchange of energy between poloidal and toroidal solar magnetic field. Ingredients: the two halves of the 22-year cycle are not identical. Typically alternating cycles show higher sunspot count. Cycle history: sunspot numbers over the past 11,400 years have been reconstructed using carbon-14-based dendroclimatology. The level of solar activity beginning in the 1940s is exceptional. The last period of similar magnitude occurred around 9,000 years ago. The Sun was at a similarly high level of magnetic activity for only 10% of the past 11,400 years. Almost all earlier high-activity periods were shorter than the present episode. A list of historical grand minima of solar activity came around 690 AD, 360 BC, 770 BC, 1390 BC, 2860 BC, 3340 BC, 3500 BC, 3630 BC, 3940 BC, 4230 BC, 4330 BC, 5260 BC, 5460 BC, BC, 5620 BC, 5710 BC, 5990 BC, 6220 BC, 6400 BC, 7040 BC, 7310 BC, 7520 BC, 8220 BC, and 9170 BC. Since observations began, cycles have ranged from 9 to 14 years. Significant amplitude variations also occur. It was first thought that 28 cycles had spanned the 309 years between 1699 and 2008, giving an average length of 11.04 years. But recent research has showed that the longest of these seems actually to have been 2 cycles, meaning that one of the two had to have lasted less than 8 years. Recent cycles. Cycle 24. The current solar cycle began on January 4, 2008, with minimal activity until early 2010. It is on track to have the lowest recorded sunspot activity since accurate records began in 1750. The cycle featured a double-peaked solar maximum. The first peak was reached 99 in 2011 and the second in early 2014 at 101. Cycle 23. This cycle lasted 11.6 years, beginning in May 1996 and ending in January 2008. The maximum smooth sunspot number observed during the solar cycle was 120.8, and the minimum was 1.7. A total of 805 days had no sunspots during this cycle. Phenomena. Various solar phenomena follow the solar cycle, including sunspots and coronal mass ejections. Sunspots. The sun's apparent surface, the photosphere, radiates more actively when there are more sunspots. Satellite monitoring of solar luminosity revealed a direct relationship between the Schwabe cycle and luminosity, with a peak-to-peak amplitude of about 0.1%. Luminosity decreases by as much as 0.3% on a 10-day timescale when large groups of sunspots rotate across the Earth's view, and increase by as much as 0.05% for up to 6 months due to factly associated with large sunspot groups. The best information today comes from SOHO, such as the MDI magnetogram, where the solar surface magnetic field can be seen. As each cycle begins, sunspots appear at mid-latitudes, and then closer and closer to the equator until solar minimum is reached. This pattern is best visualized in the form of the so-called butterfly diagram. Images of the sun are divided into latitudinal strips, and the monthly averaged fractional surface of sunspots calculated. This is plotted vertically as a color-coded bar, and the process is repeated month after month to produce this time series diagram. As there are peaks in sunspot number around 1955 to 58, James T. Struck argued for a Struck maximum, given his discovery of the peak at this point, like Maunder and Dalton's work. While magnetic field changes are concentrated at sunspots, the entire sun undergoes analogous changes, albeit of smaller magnitude. Coronal mass ejection. The solar magnetic field structures the corona, giving it its characteristic shape visible at times of solar eclipses. Complex coronal magnetic field structures evolve in response to fluid motions at the solar surface, and emergence of magnetic flux produced by dynamo action in the solar interior. For reasons not yet understood in detail, sometimes these structures lose stability, leading to coronal mass ejections into interplanetary space, or flares, caused by sudden localized release of magnetic energy driving emission of ultraviolet and X-ray radiation as well as energetic particles. These eruptive phenomena can have a significant impact on Earth's upper atmosphere and space environment, and are the primary drivers of what is now called space weather. The occurrence frequency of coronal mass ejections and flares is strongly modulated by the cycle. Flares of any given size are some 50 times more frequent at solar maximum than at minimum. Large coronal mass ejections occur on average a few times a day at solar maximum, down to one every few days at solar minimum. The size of these events themselves does not depend sensitively on the phase of the solar cycle. A case in point are the three large X-class flares that occurred in December 2006. Very near solar minimum, and by 9.0 flare on December 5 stands as one of the brightest on record patterns. The Waldmeyer effect names the observation that cycles with larger maximum amplitudes tend to take less time to reach their maxima than cycles with smaller amplitudes. Maximum amplitudes are negatively correlated to the lengths of earlier cycles, aiding prediction. Solar maxima and minima also exhibit fluctuations at timescales greater than solar cycles. Increasing and decreasing trends can continue for periods of a century or more. The 87-year and that the following cycle have a maximum of about 70 plus or minus 30 in 2023. Associated centennial variations in magnetic fields in the corona and heliosphere have been detected using carbon-14 and beryllium-10 cosmogenic isotopes stored in terrestrial reservoirs such as ice sheets and tree rings, and by using historic observations of geomagnetic storm activity, which bridge the time gap between the end of the usable cosmogenic isotope data and the start of modern satellite data. These variations have been successfully reproduced using models that employ magnetic flux continuity equations and observed sunspot numbers to quantify the emergence of magnetic flux from the top of the solar atmosphere and into the heliosphere, showing that sunspot observations, geomagnetic activity and cosmogenic isotopes offer a convergent understanding of solar activity variations. Hypothesized cycles periodicity of solar activity with periods longer than the sunspot cycle has been proposed, including the 210-year Suez cycle. This cycle is recorded from radiocarbon studies. Although little evidence of the Suez cycle appears in the 400-year sunspot record, the Hallstatt cycle is hypothesized to extend for approximately 2,300 years. An as yet unnamed cycle may extend over 6,000 years. In carbon-14 cycles of 105, 131, 232, 385, 504, 805 and 2,241 years have been observed, possibly matching cycles derived from other sources. Damon and Sinnett proposed carbon-14-based medium and short-term variations of periods 208 and 88 years, as well as suggesting a 2,300-year radiocarbon period that modulates the 208-year period. During the Upper Permian 240 million years ago, mineral layers created in the Castile Formation show cycles of 2,500 years. Solar magnetic field. The Sun's magnetic field structures its atmosphere and outer layers all the way through the corona and into the solar wind. Its spatiotemporal variations lead to various measurable solar phenomena. Other solar phenomena are closely related to the cycle, which serves as the energy source and dynamical engine for the former.